Hey everyone, I'm Austin Schuh. I'm software mentor on Team 971. So who was here last night at our workshop? A couple. Okay, so normally I like to give these workshops in the other order, but the way the time slots worked out, we had more time last night and less time today, so we'll do it backwards. Go ahead and go to the back, guys. So last night we went and we simulated a robot, this robot in fact, wrote some test cases. We were able to get it to move in simulation, and then when we tried it out on the real hardware, it worked pretty much first try, which was pretty cool. And I had never actually seen this robot until an hour before the workshop, so it was a very live demo. So today what we want to do, or in that, we had a simulation function where we passed in voltage and we returned an acceleration, and I used it as a black box. And I want to now go make that black box not a black box anymore. So we'll go and work through all the math for how do we model a motor and how do we simulate an elevator. So let's start in. So we're going to start with a simplified brushed DC motor model. Come on in. Into the back. So we'll start with a simplified brushed DC motor model. So we can model this as our motor. Can people see that effect? Yeah. Great. So this. So we have two components in our motor, and you can find these. You can almost find these physically. So our motor has a resistor in it. So this is literally the resistance of the copper windings in your motor. And then go ahead and slide it back. And then our motor has a generator in it. So when you spin your motor, it generates a voltage. So in our real motor, these are not unique components. They're distributed. The windings have resistance, but we can, without loss of generality, we can draw it this way. So then this gets us, so then the overall voltage across our motor V equals IR plus omega over KV. So omega here is the angular velocity of the motor. So it says we generate a voltage proportional to how fast we're spinning. KV is a constant for our motor, and then this is the current and the resistance. So, inside the back, standing room only. So then the second equation, so this is useful. The second equation that we can get here is we want to know how much torque is our motor going to apply. So it's actually pretty simple. So our torque tau equals the current. I'm trying to make sure I get my conventions right. Times KT. Okay, so this equation says that the torque out of our motor is directly proportional to the current, which kind of makes sense if you apply. So say we try and simplify this equation. So let's say our motor is stalled, so omega 0, and our voltage then directly gives us a current, and our current gives us a torque. So if you apply half voltage to your motor, you get half torque. If you apply full voltage, you get full torque. That's kind of something we can see in reality and go measure. So let's try and work this a little bit. I'm going to grab some numbers from, let's pick a sim. Grab some numbers from a sim and from the data sheet. Let's see if we can derive some of this. I don't have them memorized, so let's go look for them. So a sim, we have a stall torque. Go inside to the back. Just keep it really clear. Okay, so this is directly off motors.expro.com. I don't know if you haven't been there. It's probably one of my favorite sites. You can get all the constants for all the motors and do all your math there. So Sim has a stall torque of 2.4 newton meters, draws 131 amps in stall, and spins 500 RPM. So from here, we can actually calculate R, kV, and KT. Does anyone like to get some audience participation? Does anyone see how to get one of these constants? Yes?
You can set your voltage all the way up and then have it stall to get just IR. And then
Okay, so what does stall imply here?
Your omega 0.
Okay, perfect. So if we're going to check at stall, this is going to be 0. We can then look at our list here. We have a stall current of 131 amps. So that gives us an I. B, all those numbers are 12 volts. We have 12 volts. So that gives us a resistance. Okay. So great. So we got one of them. Let's see. So got that one. Can we get KV or KT? Someone else see? Yes.
Using the second equation, can we use the stall current and the stall current?
Yep. So we got 2.41 for our stall torque, and then our start curl, it's 131. Do getting close, then we got one left. Anyone see how to get KV?
You want to have a free speed. Use your free speed and then put it to the right.
Okay, so yeah, so our free speed, so for our torque 0,
Which implies that the current would also be.
yeah. So if our torque 0, by this equation, our current 0, that means this term drops out. So our voltage equals, so we can then solve this. So our omega over our voltage is KV. So we would say, people following what we just did here? See some nods, that's good. Okay, so this is pretty useful. So now we can take our motor and given a voltage and a speed, we can get out a torque. So that's useful, but what we want to do next is we want to hook our motor up to an elevator. So let's start, write some things, and then we can start working out what the free body diagram for that looks like. Okay, so we can draw a simplified schematic of our elevator. So it's got, we've essentially got a loop here with our mass on it. And then we're driving, and this one it's a spool, but we can kind of model this as a pulley, so it either pulls it up or pulls it down. So from here we have a gear reduction connected to our motor. Okay, so we can start working out the torques and speeds here. So this is gear reduction G. So we have torque on our motor. So the physics equation we're going to want to use to kind of tie this all together is we're going to get a force out of here equals the mass times the acceleration. Okay, so we got to get everything in terms of force and speed of our mass in position. So let's start on it. So let's get to torque of our pulley here. So tau motor equals torque times our pulley, and then force on our mass is going to be so the force divided by our radius, or the torque divided by our radius, gets us the force, our mass. And then we, of course, have force equals mass times acceleration. Okay. So, do we have enough equations yet, or do we need some more? It's enough to simplify everything out. Okay. Oh.
But you need a factor to account for that.
Yep. We got to deal with speeds. I'm wondering if we should start simplifying so it's a little more obvious. Yeah, let's start simplifying and see where that gets us. Substitute these in. Okay, and we can substitute this in. Anybody stop me if I mess up any of the algebra here. Easy to mix this up. Okay. We can substitute this in. Okay, so we got to here. So this has, we have the acceleration is related to the angular velocity of the motor. So we'd like to, those aren't very useful units. So we'd like to get rid of this angular velocity of the motor. So we got to convert speed of our motor to speed of our car.
So you want to use the gear reduction.
Yep. So whereas our gear reduction here made our output, made our torque higher, it's going to make our speed slower. So it's the inverse of the gear ratio. So angular velocity of our motor. Let me make sure I get the sign right. So the angular velocity of our motor, I think I got this right. Please check me. Yep.
On the MX, should there be a WKG instead of W?
Did I miss that? Yeah. Thank you. That would have been rough on our physics. Cool. Got one error. Okay. Can you check this one? Did I get the G in the right spot?
Yes.
Okay. So now we can start. So angular velocity of our motor times our gear ratio is the angular velocity of the pulley. And then angular velocity of the pulley times the radius equals the velocity of the chain or the carriage. I'll substitute that on. Great. Yes?
Question. Can you just repeat, like, what was the end thing you're trying to solve for?
So our physics is going to have an input and output. Okay. We want to get rid of all the things that aren't in that input or output list. So the input here is, well, what is the input that you apply to your motor? Yeah, so you apply electricity, which we apply voltage. Okay, it's really voltage and current, but on your motor controller, you pass it out, you give it a duty cycle, which gives you a percentage of battery voltage. Okay, so we're going to put a voltage in, and then I don't know about you, but I don't really care where my motor is. I care where my mass is. Okay? I care where the box is. I care where, depending on the year, I care where whatever we're manipulating is. So we want to get all of our physics to take a voltage in and talk about position, velocity, acceleration of the output. Okay. So here we're starting with our motor, which is awesome. We now have a motor model, but this doesn't tell us what our output's doing. So we got to work through the physics to get to, this tells us, here's the acceleration of our carriage, given the voltage and the velocity. So now that's actually something useful that we can go simulate. That was a good question, thank you. Going way too fast. Yes?
So for your convention for G, so you want to, are you trying to use the smaller G reduction or like, 1 over it?
50-50, I pick a convention every year. As long as you're consistent,
yeah,
it doesn't matter. I probably picked a different convention for every robot, unfortunately. Yeah, but I did try, so there are conventions for KV and KT out in industry. And I believe I've picked the correct convention from industry. They're just scalar constants, so you can invert them without anybody noticing in the math. So it's useful to be able to talk about them. But for, you can always double check by looking at the units on those. Okay. I guess we can talk a little bit about where to take this from here. So we're going to want to simulate this equation. So there's some useful properties here. So just intuitively, let's erase that. So intuitively, so what this? So intuitively, what this is saying is the position of our elevator doesn't matter, which kind of makes sense. There's nothing physically different about being in different positions. So what we care about is when I apply a voltage, how does the velocity change? How does it accelerate, decelerate? So this is actually going to have, this is going to be an exponential decay up to your free speed. So what this is going to look like. And the rate's going to depend on the mass. Kind of, if that makes intuitive sense. So one of the other things that is useful to be able to do is rather than solve this differential equation with calculus, we can just throw computers at this. Yes?
The x-axis exponential decay graph, is that t for the x-axis, is that voltage?
Time. This is assuming a fixed voltage. So if we just hook your motor up to the battery directly and let it go, assuming your elevator is infinitely long, it will accelerate up. So as you're not moving very fast, this term is not subtracting much. So you're going to get your peak acceleration. And as you start to speed up, the velocity term is going to get bigger. So it's going to start to subtract from here. Your acceleration is going to decrease. So you're going to get this characteristic exponential decay. So what we can also do is, so we want to solve this, we want to simulate this. One of the easiest things to do nowadays is we have big computers that can execute a lot of calculations, so we can just do this numerically. And that's a great input to our simulations. So what the trick here is, say we have, and this is an entire field of study, so you can go study a lot more of this in college if you get excited about it. It's numerical analysis. So if we have, say we have some acceleration as a function of time. Okay, and we want to ask, if we start at a velocity here at the start of time, what velocity are we at a different point in time? Okay, so this would be a much easier, so say instead of it being a curve, it was a straight line. Okay. What would be the equation to get you from the starting velocity and the time and the acceleration at the end?
It would be acceleration times time plus the initial velocity.
Yeah. So it would be start velocity would be v1 equals v0 plus delta t times the acceleration. Okay. But that's essentially finding the area under this curve and adding it. So we can make this more complicated. So if we make this a curve, okay. So if we went and we draw a bunch of little boxes, what we can do is for each of these will be, say, delta ty. We can take the value at the start times delta t, and we can just add up the size of each of the boxes. And you know, it's not quite right. You can see here it's off a little bit, it's off a little more there. But it's by and large, it's pretty close. And it gets better and better as our boxes get smaller. So we pretty much have supercomputers in our pockets nowadays. Phones are amazing. Laptops are amazing. So you can just make time small enough that it doesn't matter, and your simulation will be good enough that you won't be able to tell the difference. So that's one of the tricks we'll use to simulate this stuff. And then, you know, once you go from acceleration to velocity, you can go from velocity to position using the exact same mechanism. So this is how we took our model last night and we're able to simulate it. I am at the end of my material. If people have questions, I can also bring up, we had the data sheet for the motors. We can bring up some of those data sheets and explore a little more, because that's useful. Yes?
So in the MX double dot,
Yep.
are you taking into, is there a difference in taking account of gravity here, or is this like?
We can take that into account if we wanted, where we had F equals ma, the force being only force plus gravity. For the most part, I found you can ignore gravity in a lot of the control stuff we do. You want to come up with the simplest possible model that works. But if you think it might be an effect, you can go model it and see how it changes things. We tend to make gear things such that gravity is, say, 10% of your load, 10, 20%, which is, you can start to get away with ignoring it. Did I see a hand?
Is that for looking at robots that have a constant force spring?
Yeah, you can model that. So if you put up constant force spring, it kind of negates gravity.
Okay.
But yeah. I think if we were to add gravity, it would be minus. Is that right? Yeah, that's right. Yes, sorry, didn't see it.
What was the website again you were getting all the numerical values from?
Great question.
Model.
We have to know.
Can someone hit like one of the lights or something? It's not gonna work. So this is motors.vex.com. We use this a huge amount every year. So the guys at Vex went and they did a bunch of testing on a bunch of motors, and they gave us all the numbers, which is really helpful. So we can see, for a sim, here's our free speed, free current, stall current. See that for a bunch of different motors, see how they stack up. One of the cool things we can drill in, so let's go look at a sim in a little more detail. Okay. So we can actually see this graphically. This is representing the equation that we just derived in a different form. So we can look at this whole chart's assuming you're applying 12 volts to your motor. So we can look at torque as a function of speed. So this is as your generator is spinning faster and faster, it's going to generate more voltage. So it's going to reduce the amount of current that you can apply, which reduces the torque. So we can see a linear relationship between current. So when we're stalled, we get all the torque. And when we're free speed, we have no torque. It's a linear relationship. So you can see that here. Power is torque times speed. So you can get a parabola there. Yeah, a bunch of really good data here. One of my other favorite plots, which we use a huge amount, is the locked rotor test. So somebody tried 2 volts, 4 volts, 6 volts, 8 volts, 12 volts on a motor, stalled the output, and see how long, or waited until smoke poured out. So smoke pours out right here. So this actually tells you how long your motor will survive as it warms up. So if you apply 12 volts, your sim lasts 40 seconds. And then I'm told smoke comes pouring out the sides and they're never useful again, and the smell permeates the building for a while. On a sim, if you apply 2 volts, you're going to get bored. Also, and this is interesting, you can see, say we apply 6 or 8 volts. As the sim warms up, it gets weaker. So the magnets start having trouble, and the windings have trouble, and the resistance goes up. So, I don't know, I find this hugely useful because we try and design the holding current, the current it takes to hold an elevator up at a certain height so that it won't smoke it. And this chart tells you when it's going to smoke it. Yeah, other questions?
So if you were to take account efficiency of the gearbox, where would you add that factor into the equation?
It would reduce the output torque.
So you would just append it to the torque.
I would scale it. I would take the torque and multiply it. Gearboxes, what he's getting at is gearboxes aren't perfectly efficient. If you put a torque in, you don't quite get it out. There's a little bit of friction, and that steals some of your torque, and steals some of your power. Yeah.
And how about multiple motors on one motor? On like a drivetrain or something? How would that? You just multiply the torque.
You can make a super motor where you add the torques together, or you could actually do it in your free body diagram, but you're going to get the same result.
But it doesn't matter if like the motors are oriented like parallel or like on the same side, right? It would just all add together.
It comes down to your free body diagram. If you have 2 things applying a torque to another gear, and the torques add together, then it's equivalent to adding, no matter which way the motors are pointed. I see a question?
Yeah. So are these lessons all of them going to be posted on the website?
Yes.
Okay, cool.
So you can watch it again and again.
What's the website? Citrus Circuits YouTube channel.
Yes?
What happens after 300? It doesn't.
Aaron got bored. Aaron Hill, who's actually mentoring 97.1 now, ran a lot of these tests on a Dyno FX when we worked there. And at some point, this is past the end of your match, so people don't really care anymore. Looking at the slope here, I don't think anything's going to happen. Yeah, the slope, like the road. I think it goes down a little bit. Yeah. Yeah. Any more questions, or are we good? All right, thank you, everyone. I'll stick around if you have more questions. All right.